So we had part one where we went through the statements of the kinetic molecular theory, and we were talking about temperature and kinetic energy and how they're related, and we were talking about the distances between molecules and how they're always moving and they collide with elastic collisions. We used that to explain the behavior that we see on the macroscopic level of Boyle's law and Charles's law. Now we're going to look at part two, and we're going to specifically kind of narrow in on the connections between temperature and velocity. We know that the average kinetic energy, and that bar means average, is equal to 1/2 mass times the average velocity squared of those molecules. So we know that relationship. We know that when the temperature goes up, kinetic energy goes up. And as kinetic energy goes up, the only thing that can be changing is the velocity. Molecules aren't getting fatter or skinnier. They're not changing. It's how fast they're traveling. So we're going to be looking at that connection here with this lesson. Forgot my remote again. Okay. So here is a graph. And let's look at what's on this graph, both along the y-axis and the x-axis. Let's start with the x-axis. It's showing the average speed of the molecules, and along the y-axis over on the left-hand side would be the relative number of the molecules. Now I'm going to go to the screen and I'm going to write on the screen, and we're going to talk about this image for just a little bit here. When we see a mountain like this peak here, okay, we need to be able to read what it's telling us. The average is a little off center, little off center down here, and we could say that on average the molecules of oxygen are traveling about approximately 400, and the units are meters per second. Okay? Now what are we doing? We're keeping all of these at the same temperature. So each one of these are at the same temperature. So in order to keep the average kinetic energy for all of these exactly the same, but they're moving at different speeds, we know that their masses are different, or I should say it another way. Oxygen has a mass of 32, nitrogen 28, okay? Water 18, so they're getting lighter and lighter and lighter as we move this way. So the mass is changing, but they're all at the same temperature. And if they're all in the same temperature, then this has got to be getting bigger. So if this is getting smaller, this has got to be getting bigger to keep up with that, so that they all have the same average kinetic energy. So the light molecules have on average a much faster speed. So the oxygen, average speed 400 meters per second. Let's take helium. Helium, a little off center, would be the average. That'd be here, and that's about 1200 meters per second. So that's how you would read this. A lot of students think the height of the mountain means that this is more, or going faster, but no. It is where the height is gives you the average speed of those molecules. Okay, so we think about these comparing molecules at the same temperature. The kinetic energies aren't changing, but their velocities are changing. Now let's look at this graph, a little bit different. Here we're looking at the same substance, okay? That's not changing, and in every case it is a nitrogen, okay, situation. But they're at different temperatures. So 273, that's around room temperature. I mean, no, it's not, 0 degrees. Then we have 1000 K and 2000 K. All right, so what has to be changing of these guys? They are changing their kinetic energy, but it's the same molecule, so their masses are not changing. So they all have the same mass because they're all nitrogen, but if they're at different temperatures, then it has to be, and we'll once again write our equation. If the mass is not changing, if the kinetic energy is going up because the temperature is going up, then the velocities have to be getting greater, moving faster. Okay, so what's the average speed of these guys? That's down here, maybe around 400 meters per second. So we raised it up to 1000 Kelvin. Okay, this looks like it might be around 900, and we're up to 2000, and we have maybe 1200. So our speed is getting greater. Key statement: kinetic energy increases with the temperature. As the temperature goes up, the kinetic energy goes up. If the kinetic energy is going up, it's because the velocity is increasing. And the increased speed, key point, is all due to the increased kinetic energy is all due to the increased speed of the molecules. So we have two different things graphed. I'll flip back to the previous one here, okay? Here, there are different molecules, but they're all at the same temperature, okay? Over here, we have different temperatures, but they're the same molecules. And you ought to be able to understand those graphs and how they relate the speed of the molecules to what you see here. Okay, now, root mean squared speed. With root mean squared speed, this is a way of determining the average speed of the molecules, okay? You cannot do a typical average. What's a typical average? A typical average is adding up all the speeds and dividing by how many you have. You cannot go into the gas chamber and look at each molecule and say, how fast are you traveling, how fast are you traveling, how fast are you traveling, add them all up and divide by how many molecules you have. That would be an impossible way of coming up with an average speed. So a root mean squared speed is a derived equation that is utilizing this equation and another one that we're not going to get into right now to give us this equation that we're going to see here in just a minute. If you want to look at the derivation, and again, like I said, I'm not going to go into the derivation, but it's really handy to look through the derivation, because when you look through the derivation, it helps you remember the equation itself, because the terms make sense why they're there. So here's the equation. Okay, that's not the equation. There's the equation. That RMS at the bottom, that means root mean squared, okay? It's an average calculated by this square root here, and it is 3 times R times T, and that M on the bottom is the molar mass. Now let's talk a little bit about this R. This R is the ideal gas constant, but it has different units. It doesn't have the units that we're used to. Let's write the one that we're used to seeing and see how it's different. In this chapter, this has been the R that we've been using, liter atmosphere per mole Kelvin. This is the same R, but it's with different units, 8.314. The liter atmosphere is a unit of energy, just like the mole is a unit of energy. So while these look very different, they're both R's, but in different unit values. We need this one because this is the one that's going to let our units cancel, and we'll see that as we work through a problem. So, recommend looking at the derivation so that you can remember this equation and be able to utilize it. All right, so it says here in red, watch your units. Very important to watch your units. And in order to watch the units, you have to be able to know what the base units of a joule are. A joule is a derived unit. So we need to replace that joule with a kilogram meter squared per second squared. Okay? This and this, the same thing, because a joule is a kilogram meter squared per second squared. Now units are going to be able to cancel for us as we work through a problem. We're going to calculate the root mean squared speed of N2. So the root mean squared speed, according to the equation, is the square root of 3RT divided by the molar mass. We have the square root of 3. The R we're going to use is 8.314 joules per mole Kelvin, which is the same thing as kilogram meter squared per second squared mole Kelvin. Okay, so all of that part there is the joule part, joules per mole Kelvin. So that's that. So what does temperature need to be in? Well, we've got to cancel with this guy. So that tells me the temperature better be in Kelvin, and 25 is 298 Kelvin. So that's in the numerator underneath this radical, and in the denominator is the molar mass. Okay, that's the molar mass of N2. So the molar mass is of N2. It's 14 times 2, or 28. And with an extra couple sig figs, we'll call it 28.02, and that's in grams per mole. So when we go to the periodic table and we look up that, well, the moles are canceling fine, okay? The K's canceling fine. There's nothing to cancel with those, but the kilogram and the gram can't cancel. So when it says in red, what's your units? This is where you got to be really careful. Make sure we don't keep it in grams, but have it in kilograms so that we can cancel with those kilograms. And a kilogram is 1,000 grams. So now the grams are canceling, the kilograms are canceling, and we're left with meters squared over seconds squared. When we take all of this and put it in our calculator and take the square root of it, we get 515. And if it's meters squared and you take the square root of that, you have meters. If it's seconds squared and you take the square root of that, you have seconds, and that's a speed, 515 meters per second. So in 1 second time, a molecule of nitrogen on average will travel 515 meters. That's going pretty fast, okay? And that is the root mean squared speed and how you calculate it and what I mean by watching the units. Now, you've got a couple options here. One is to memorize what a joule is. The joule is the same thing as a kilogram meter squared per second squared. So that's the same thing as a joule. That's a handy thing to memorize, and that is going to be useful many times in the future. Or you can memorize that when you use this equation, you better make sure your molar mass is in units of kilograms per mole and not in grams per mole. That's just handy for this equation and nothing else. So you can choose which way you want to go. I always like things that I have to memorize that I can use a lot in the future, so I choose to keep this straight in my mind of what a joule is. All right, next problem. I want you to work this one. Now, I want you to think about this equation and answer which one of those would have the higher average root mean squared speed, the N2 or the O2. Stop. Think about it, choose one, and then resume. Okay, hopefully you thought about it, and you came up with it is going to be the oxygen. No, you wouldn't come up with the oxygen, you'd come up with the nitrogen. Why? Well, let's think about this for just a minute. There's a lot of different ways you could have answered this question. One way you could have answered this question is go back and look at the graph where I showed you if things are at the same temperature, what happens to the average speed as the molecules get lighter. And we saw that the lighter they are, the faster they have to travel. The lighter they are, the smaller this number, the faster they have to travel to have the same kinetic energy on average. That would be one way to think about it. Let me say that again. We know between nitrogen, which is 28 grams per mole, and oxygen, which is 32, they can't both be 28, 32 grams per mole, that this is the lighter of the two, okay? If this is smaller between the two, then the speed has to be greater if they're both at the same average speed. So that'd be one way to think about it. Another way you could think about it would be with this equation here, okay? As we think about it on this equation, where does molar mass come into play? It comes in play in the denominator. As you divide by a smaller number, you're going to get a bigger number here. So a smaller molar mass would lead to a greater speed, or a larger molar mass would result in a smaller speed. Okay, whichever way you want to think about it, one way to kind of latch onto that is to think about, you know, who typically runs faster. All right, the big lineman who's big, or the running back. Okay, they're typically smaller and more agile and can run faster. I don't know, that's just something to hold on to. But typically, when you're smaller, you can travel faster in human terms, and big lumbering people typically don't run as fast. That's not why at all nitrogen is going to be faster than oxygen, but it's just kind of a connector that you can make to it. Okay, the last slide I want to show you in this lesson is the discussion of diffusion, and diffusion is one that I want you to read about. The equation that you see at the bottom of the screen relates the rate of diffusion or effusion to the molar mass. You can see that it is a kind of a reciprocal relationship. Remember, with speeds of molecules, the molar mass was on the denominator, and as the mass got bigger, the speed went down. Well, if the speed goes down, the rate goes down. Rate is like miles per hour. So read through that section as you're learning to do and take notes on it, and that finishes up this video lecture.